So what did I do? 1, 2, 3, 4. Is that what I did? So what you have here is that x1 is 1. When we say this n runs from 1 to infinity, the x1 is 1, the x2 is 2, the x3 is 3, so forth. When we write xn sub k like this, notice that the index, I should have written that. Did I write that like this? Yeah. Or did I try to imitate Bartle? Okay, so this tells you that this is what's running. This is the thing that's changing. The k starts from 1 and goes up to infinity. And so when k is 1, you have this term right here. Did I pick out just the evens? Yeah. Okay. I did a different hairstyle today, so I'm not sure what I did yesterday. You know, when you change your hair, you kind of forget what happened the day before. So you get 4 is the next one. This is k equals 2, dot, dot, dot.
The same haircut. Except for 3 period.
I went to Suits PT and I thought I'm the only one here that just ruined my straight hair. Everybody else seemed fine. But if you look at this, the k is just telling you what element you are in the new sequence. It's a new infinite sequence, and they're all infinite. I think Dr. Moen probably told you that, like these are infinite. But the n indicates that it's coming from objects in here. That's what the n stands for. So the n means relates back to original sequence. And I forgot who sent maps onto. Is it Sam? Yeah. That's kind of, you're just remembering that this k is dependent on the original sequence. That's what the n is telling you, that it's coming from an original big sequence. They're both big. They both have the same number of elements. But, so that's all the n is doing. It's relating back to here. So you would use s here and then an n here. It's just letting the reader know when they're looking at it that you're taking from this original sequence, which is indexed by my symbol n. That just tells you that it's coming from that original sequence. And the k's are just, and then you could list them out here too like this. N sub 1 is equal to 2. N sub 2 is equal to the 4th element. So this is a bad example, actually. This just means second element. It's telling you which element number to pull from. You can actually yank the element number. I should not have made them all even because that looks confusing. But that's what you're doing. Right? So this is the next couple classes are the heavy hitting theorems for real analysis. I was actually looking at making one of those custom t-shirts that says, I survived the proof of Bolzano-Weierstrass without any topology. These are the big theorems that we're going to get from here, from real analysis, that if you took a real analysis class anywhere, they'd expect you to know those things. So I love them, by the way. Probably any pure mathematician does. Dr. Moen, you probably hear her own passion for just pure mathematics. She's in here. So she's going to love this too, and she's going to be jealous that I get to be the one that presents this. All right, so first one clear, what to put down for number 1?
Wait, so is nk itself a sequence? And that sequence?
Nk is just an index. So like that's why I said this is a bad example. So this is n1 means second element from first sequence in this case. And then what is k exactly? K is just if I have k equals 1, it just means the first element of my new sequence. K equals 2 is the second element of my new sequence. So from the original sequence, I've extracted from it a baby sequence. And this index here, when k is 1, tells you it's this guy up here. K is 2 is the second element here. So the new index for your new sequence.
Like hypothetically, you can make a sequence n sub k. That represents all the indices of x that you're going to be indexing.
You need to repeat the whole original sequence, you mean?
No, so you got like, if you made a sequence n sub k, then at k equals 1, n would equal.
Well, we don't know what n equals because I could have said pick every third one or pick every.
Two.
Right.
That's what you're doing. It's the second index. And then at k sub 2, n would
No, this n is only a symbol that means you're extracting from the sequence. So this n is not running, only your k is running. Yeah, no, you're not setting it equal. It's just that it's just one of those indicators that's letting you know that it's coming from this original sequence. Ready? Ready for monotone? So Dr. Mon presented for you what a monotone sequence was, the definition. I repeated it for you just so you know that. I got in a big argument with someone on Twitter because they were talking about increasing and decreasing sequences. And I said, well, we call something that is, when it's less than or equals to, we say non-decreasing and non-increasing. And they said, well, in English, we say it this way. And like, okay. So back and forth we went. But then I looked in Bartle, and he has increasing as meaning what we typically say as non-decreasing from your Stewart textbook. So I guess and he's not British, so the British person won. So here's the first big theorem, monotone sequence theorem. So if I have a sequence of real numbers, there's always going to be a subsequence that's monotone. I have slightly different language than your textbook because I was on a plane when I wrote up my notes and I didn't open the textbook. So, but it's this, I would have looked back, it's the same meaning. So I'm going to prove this for you. It's pretty remarkable. I'm going to have you jump around actually, and do some different examples. Why don't you start with number 4 on your in-class assignment? It seems really remarkable actually if you think about it. A sequence doesn't have to have a pattern. You take the digits of pi and make a sequence out of it. Think about that. Like from this theorem, it says that that's supposed to have a monotone subsequence. How would you get that? So start with number 4. Talk amongst yourselves. Like this is one that you really want to think through. And then after you talk about this, I'll prove this theorem and then we'll do some more in-class work.